Hi friends, this video we are going to see what is meant by residue and how to calculate the residue. Now we start with what is the definitions of residue. Let A be an isolated singularity for the given function f of z, then the residue of f of z at A. So A is some point in the complex plane, okay, and A is defined, the residue of f of z at A is defined to be the coefficient of of 1 over z minus a in the Laurent series. Series expansion Laurent series expansion of f of z about point A, and it is denoted by residue of f of z. So here this is the residue. That means I want to write the function f of z about a singular point A. I want to represent in the Laurent series. So little detail means I want to represent f of z as a singular point at A. So I can write the summation n equal to 1 to infinite an times z minus a the whole power minus n plus summation n equal to 0 to infinite bn times z minus a the power n. So residue means we take it as a1. So residue of f of z at a is defined as a1, because I want to put the n equal to 1, that is an divided by z minus a will come. So the coefficient of 1 over z minus a is a1. This is the my residue of f of z. Okay, so now whenever a is a isolated singular point, this is the most important. Non-isolated singular point we cannot represent as a, in terms of Laurent is very difficult. So whenever a is an isolated singular point, then we can proceed. So now first step we see some example of residues. Like f of z equal to sine 1 over z. So clearly z is equal to 0 is an isolated singular point, correct? So I can represent in terms of Laurent series. So Laurent series of sine 1 over z Sine 1 over z is equal to 1 plus 1 over z minus 1 over z cube times 3 factorial plus 1 over z power 5 times 5 factorial and so on. Correct? So this is my Laurent series. What is the coefficient of 1 over z minus a? Here a is 0. So our point a equal to 0 here. So we represent. So the coefficient of 1 over z minus a is 1. So residue of 1 over z at 0 is 1. This is my residue. Now next example, another example we see, example 2. F of z equal to exponential of z divided by z square. So now I represent in terms of Laurent series exponential of z square. So first I want to find singular points. Singular points z is equal to 0. It's an isolated singular point. So I can represent in terms of Laurent series. I will get it as 1 over z square plus 1 over z plus 1 over 2 factorial plus z divided by 3 factorial and so on. So clearly the coefficient of 1 over z is here. This is my the term, correct? So then my residue of f of z is exponential of z divided by z square at 0. 0 is clearly 1. So we cannot, every time we cannot express the every function in terms of Laurent series. So that is why we have some tool. Okay. These tools are only for pole. Okay. Whenever you have the essential singularity, you have to use only the Laurent series only. Whenever it is a finite, because a pole order m, we can use the following formulas. So we have, I will give the 4 formulas. The first formula, if this is a formula number 1. Okay, so I put it as this is a formula 1. If a is z equal to a is a simple pole, for f of z. The simple pole means you already know what is the pole. The simple pole means it's a order, it is a isolated singularity, the pole of order is 1. Then residue of f of z a is simply limit z tends to a, you multiply z minus a times f of z. Okay, this is the formula number 1. Second formula, the same you take it if z is equal to a is a simple pole. for f of z, and f of z you can represent in terms of g of z divided by z minus a, where suppose you know that the g of x is analytic, where so g of z is analytic, at a and g of a is not equal to 0, then residue of f of z, that is g of z divided by z minus a, is nothing but simply g of a. You think the first formula and second formula very simple, both are one. If you know the first formula and second formula, you can derive, both are same only. Now you go for the third formula. So this formula is very useful, since it is whenever the trigonometric function will come, this plays a very crucial role. This formula plays a very crucial role. This is also for simple pole. If z is equal to a is a simple pole for f of z. So here I am using for simple pole for f of z, and f of z you can represent in terms of h of z divided by some k of z, where k of z and h of z both are analytic, at a, and h of a is not equal to 0 and k of a equal to 0, you can write then residue of f of z at a is nothing but h of a divided by k prime of a. So you want to take the derivative with respect to z and substitute that value is a. Here the prime means, so k prime of a means nothing but dk divided by dz at z is equal to a. That's it. This is the third formula. Now we are going for the fourth formula. So the first three formulas for simple pole, but the fourth formula is for the pole of order m. Okay, let a be a so a is in a complex number. Okay, a be a pole of order m which is strictly greater than 1 for f of z, and let f of z equal to some g of z divided by z minus a the whole to the power m, where g of z is analytic at a also, and g of a is not equal to 0, then residue of f of z at a equal to, so if it's a number, you want to take g of m minus 1 times you want to take derivative with respect to z at a divided by m minus 1 times factorial. Here gm minus means g m minus 1 of a means derivative of m minus 1 times of g of z at z is equal to a. This is we define as, okay. So this is the 4 formulas will be there. So please clear, it is for the 4 formulas only for isolated singularity with the singularity classification is pole. Whenever the essential singularity means you have to use only the Laurent series. Directly you want to use the definition. Okay. Now we solve some problems using this result. First problem. Calculate the residues of z plus 1 divided by z square minus 2z at its pole. Okay, so how I can solve? Let f of z is equal to, so your f of z is z plus 1 divided by z square minus 2z. So this means I can represent as z plus 1 divided by z times z minus 2. So this implies z is equal to 0 and z is equal to 2 or simple pole for the given function f of z. Okay, so these are the simple pole only, so I can use the first or second result. Okay, so z plus 1 divided by z times z minus 2 0 is nothing but, you can use both first and second or third formula. So I will comfort with the first formula, z tends to 0, so simply multiply z and z plus 1 divided by z times z minus 2. This is from the formula, so you want to limit z to, so this is nothing but this z and z cancel, so you will get this minus 1 over 2. Similarly, residue of z plus 1 divided by z times z minus 2 at 2. Simply apply limit z tends to 2 z minus 2 times z plus 1 divided by z times z minus 2. So this is nothing but 3 divided by 2. These are the residue of the given function. So this is a simple pole. Next problem is, Problem number 2, example of problem number 2 we take. Find the residue. So they will given now where you want to find. Find the residue at z equal to 0 of 1 plus exponential of z divided by z times cos z plus sin z. Okay, this is the function. So now I want to proceed with, so first step, these are the simple pole or not I want to check. So how I can check the simple pole? So the given function f of z, I can write it as a p of z divided by q of z. Both are analytic at origin. Yes. Now what is the q? Find the zeros of q of z. So this equal to z times cos z plus sin z equal to 0. So clearly z is equal to 0. This is the one of the otherwise. So you can choose z times z 0. So z is equal to 0 is the. Now I want to find the 0th order of 0 is, suppose I take q prime of z, so what will come? So cos z plus minus z times sin z plus cos z. So whenever I put q prime of 0, this is 1 plus 1 is 2, it is not equal to 0. So this implies q of z as 0 at z is equal to 0 of order 1. So this implies the q of z is a, so this implies f of z at z is equal to 0 is as a simple pole. Simple pole. So in this case you can use the first and second formula. It's very tricky. Okay. Now I am going to use the third formula. What is my third formula? Suppose I write f of z equal to h of z divided by k of z, where and the residue of f of z at a is h of a divided by k prime of a. Using this result means the one step answer. Okay, you can get the answer from the first two formulas also, but this is very easiest way. So what is already I find what is the q prime of a is 2, correct? The q prime of 2 is 2. Then h of a, that is p of a is 2. So this implies residue of f of z is at 0 is simply 2 divided by 2. This is 1. This is the residue of the given. So similarly you can do for the other functions also. Now we are going to find one more example. That is because the pole of order m I didn't do it. Okay, that's why I do the one more problem. Problem 3. Find the residue of of exponential of z divided by z square. So we saw this example, correct? We already find what is the residue is from our Laurent series. We expand, we get it, the value is 1. Using this formula, how I can get it? So I want to use this, the pole of order is 2. So m is, that is m equal to 2. So using this, the third result means I write it as f of z is equal to g of z divided by z minus a the m. That formula, that is g of z is here is exponential of z and z square. So this is m equal to 2. The residue of f of z is g m minus 1 times derivative at a divided by m minus 1 factorial. Our value is here, m is 2 and g is exponential of z. If one times only you want to take derivative, that is exponential of z is exponential of z at z is equal to 0 divided by 1 factorial. So exponential of 0 is 1. So the residue of f of z at 0 is, this is residue of f of z, that is given function at 0 is 1. This is we already seen in our first example itself. I hope you understand what is the residue and how to calculate. Thank you for watching this video.